just like we did momentum charts for linear momentum, we can do something very similar for angular momentum problems. So to demonstrate that, I'm going to use this example of a helicopter. And we're going to look at the momentum, the angular momentum exchange of the blades and the helicopter itself. So just like in linear momentum problems, when we're dealing with systems of objects with different angular momenta, if we can enclose everything within the system and then say our net torque is 0, which would mean that angular momentum is conserved, or that just, there's no change in our total angular momentum for the system, meaning that any change happens just by different parts of the system exchanging angular momentum, or we can have some net external torque, in which case something is adding angular momentum to this system, and there can be a change in the total. So let's figure out how to apply that to this helicopter scenario. So let me box this off to the side. So here we have our blades. Let's say the blades are rotating from this perspective counterclockwise. And I keep saying this from this perspective because, again, it does matter. Not everyone would agree. And, people sitting on the other side of the computer screen would think that these blades are rotating clockwise. So these are rotating counterclockwise. And the way we describe that is if we use our right-hand rule, wrap our fingers with these arrows, that would be out of the page. So the initial angular momentum for the blades is out of the page. So let's go ahead and make a momentum chart. So it looks very similar to our old ones, except now instead of P, we use L. So we have our L initial, our delta L, and our L final. And as our system, I want to include the blades as one piece, the body of the helicopter as another, and then we'll have our total. And because I made this choice, there is no net torque, no external torque applying. It's just these two things that are free to spin. The helicopter is in the air. So let's say the helicopter is just floating. It's not moving up or down, forward, back. It's just staying in the same place, floating in the air. So like I just said, net torque is 0, so that means our delta L total is going to be 0. Now, what does our initial setup look like? Well, think about what a helicopter does when it's floating. The body is still, right? We don't want all the passengers inside to be spinning around, so we'll give an initial angular momentum of 0 because the body initially has an angular velocity of 0. It's not rotating. And the blades, like we just said, those are rotating with a angular momentum vector out of the page. So that looks like there's our vector symbol for out of the page. I'm not going to worry too much about the magnitude of these. Our into and out of the page symbols aren't super great at describing that. We would need arrows with lengths, but since we're just doing a qualitative explanation, it's not super necessary. Okay, so now our total initial angular momentum is just the angular momentum of the blades or out of the page. And in this initial state, without any change, this is a happy equilibrium, right? There's no external torque that's required to keep the blades spinning. They just are spinning and the helicopter body is still. But now let's say the helicopter wants to go higher up in the air. In order for a helicopter to go higher up, to rise off the ground, the blades need to spin faster, right? So now the pilot's going to press some button or move some joystick, and these are going to move faster, which I'll represent just by lengthening these arrows. So we know that the delta L for the blades is also going to be out of the page, right? If they already were moving in the same direction, they just went faster, then we'll add some angular momentum in that same direction. So whatever angular velocity vector was pointing out of the page got longer for those blades. Now we know, since our total delta L is 0, if the blades had a change out of the page, the body must have a change into the page. And now we can quickly just finish this off. out of the page plus out of the page is out of the page. This just means the blades were spinning, then they sped up, and now they are spinning faster in the same direction. For the body, that means the body was still, and then it started spinning, and this angular momentum vector into the page would represent motion that is clockwise from our perspective. I'll let you use the right-hand rule to check that. So now the body is rotating, and our total, we know, well, out of the page plus 0 is just still out of the page. And this is where our into and out of the page vectors are not super descriptive, because out plus in could be anything depending on their magnitudes, but we know that the blades have more angular momentum out of the page than the body does in, because they started with this initial. So our total stays out of the page. Again, it does not change from our initial because there's no net torque. However, this situation is not really what happens, right? When helicopters want to go higher up in the air, the body doesn't start just whipping around in the air, right? We need something to prevent that. So this is what would happen if this was the design of a helicopter. Fortunately, this is not the design of a helicopter. Helicopters have another set of blades on the tail here that's oriented in the plane into and out of the page. So these are spinning perpendicularly to the blades on top of the helicopter, pushing air to create a force either to the left or to the right. So this set of blades here can actually counter the rotation that is created from the system we just set up. So let's see how. We'll go back to our initial setup where we only had the helicopter hovering in the air, right? So now the blades are spinning, body is still, that's fine. But now we do have some potential for net torque, because we have these blades here. They can apply a force to the left or to the right. They have some distance r from here. So we have all the, and I should write these are forces, potential forces. So there's some potential for torque, right? Torque is F perpendicular r. These are already perpendicular. So clearly some net torque can come into play and change the angular momentum of this system. So let's see what change we would want. Well, we still want the blades to speed up, right? We still want to go higher in the air, so we'll get some delta L that is out of the page. But now we want the body to have no change, right? This is our desired result, because we want to go up into the air without making all our passengers rotate super fast or rotate at all. So if that's the case, then our delta L total needs to be out of the page, right? In order for this to be consistent, which means the last row is also just out of the page. So in this setup, now we have the blades that just sped up, and as a result, the angular momentum of the helicopter increased, and the body did not have to have any change because that increase came from a tau net. This came from an external torque, not from the body counter-rotating. So let's figure out which direction this extra set of blades needs to create a force. Well, if we want that net torque to be out of the page, then we'd want the rotation, then we'd want the force to be applied in such a way that, well, if we use our right-hand rule, out of the page means rotating in the direction of these blades here. So if we want to rotate it in the direction of these blades, then we need to push it in this direction here, right? If we push the end of the helicopter this way, then it will rotate that way. Well, in fact, we don't want that to happen, but really we're counter-rotating. Remember, the helicopter wanted to rotate clockwise, but we are stopping it from doing so. So what these blades are actually going to do is spin and push the air to the left, right? So here's the air over here. The blades will spin and push air to the left and rotate it this way. Apply a torque that is out of the page. And I'll let you kind of play around with the right-hand rule and see why that is. So these blades, again, we're not worried about their angular momentum right now. We're only worried about the force that they produce by pushing on the air, and that force that they produce is this way. So if we're very specific, this is the F on air by blades, right? This is the direction it pushes the air, and this here is the F on blades by air, right? That's actually how helicopter blades or any blades or wings or stuff work, is they apply a force to the air, and as a result, the air applies a force back. We'll talk about that next week when we learn about Newton's laws. But for now, we're just concerned with the angular momentum part. Now, since these blades are rotating in another direction, they are going to introduce their own angular momentum. In this case, if the blades are spinning in the plane that we're talking about, then the angular momentum vector will be to the right or to the left. So we will have, in a different direction, some net torque, some change in angular momentum due to that, which might cause the helicopter to tip forward or backward. But for the purposes here, we'll just assume that the balance of the weight is such that it's not significant. The helicopter is not going to flip end over end. But if these blades here were really big or really heavy or something, and they created a really large angular momentum vector, for instance, that was to the left, and remember, if you point your thumb either to the left or the right, whatever, your fingers are curling into and out of the page, which would mean this helicopter is flipping head over heels or reverse than that. But we would need that if this was created, there would be an equal and opposite angular momentum vector from the helicopter. But since we know that angular momentum is equal to the moment of inertia or rotational inertia times angular velocity, these blades probably have a really low rotational inertia because they're small, and a really high angular velocity because they're moving really fast. And the result, the exchange from the helicopter, so that would be the angular momentum vector for the blades, and then for the helicopter, so we'll write LB, for the helicopter, LH, same thing, except the helicopter has a huge rotational inertia, and so the angular velocity that it has as a result would be very small. So it would have a very small effect, just like when two objects collide, one that's very heavy experiences a much smaller change than the one that's very light. And then there's also gravity that comes into play, but we don't have to worry about that. This was mainly just an example of angular momentum exchange. Angular momentum charts, again, there's just like linear momentum charts, you'll never have to use them, but they are a great organizational tool if you're trying to figure out what's going on in a problem.